Right, in 2.2.3, we have Hindu lattice method. Lattice method of multiplication was one of several techniques developed in ancient India to compute the product of numbers. The method later spread to the Arab world and eventually to Europe, where it became known as lattice multiplication. Right, historical records dating back to around 800 BCE indicate that Indian mathematicians emphasized reducing multiplication to a series of additions, a principle that underlines the lattice method. Right, and so you can read the historical note there. So procedurally, what we do is we make a series of rows and columns corresponding with whatever the values are, the factors that we're going to multiply. Then we diagonalize them. So we split each cell in a diagonal from bottom left to upper right. And we populate this with particular values. Right? So you'll see the example here, which I'll carry you through in a second. Right? But if I have the digits 1, 3, 5 multiplied by 12, so 135 times 12, I would put 1, 3, 5 across the top and 1, 2 down the side. Right? Then in the bottom, I guess, triangular region, and it's a little offset, but this should actually go through the points. It's not really perfectly rectangular, but I want to be a little bit more nitpicky about it. It would look something like this. Yeah, it's not going to be perfect, but kind of limited by the technology, or at least the formatting. But the bottom triangle is what you would get when you multiply each value on top by each value on the side. So 1 times 1 will give you a 1. All right, then we're going to do 1 times 3, gets you a 3. And then we do, 5 times 1, which would give you a 5. So 1 times 1, 3 times 1, 5 times 1. Then we do the same thing again, working from left to right. 1 times 2. So that's going to be 2. 3 times 2, which would get you a 6. Then 5 times 2, which would get you a 10. Right? But each portion of a cell or rectangular area only allows for one digit. So if I have a 2-digit number, I would write it like this. So that would be 1 times 10. All right, 1 times 10, 1 and 10. Right? And so what we then do is we add along the diagonals, right? So we have several diagonals here, and I can show you the progression, but I'll just do it right here. So we have right here, this would be one of the diagonals. That would give me a result of 0. Then another diagonal. I'll just try to get a thicker little highlighter here. So I would add these values together. Again, I only want one digit, so we'll carry whatever the remainder is. So 6 plus 1 is 7, plus 5 is 12. So I'd put a 12 here, or 2 there, and a 1 here, showing that that's carrying over to the next column, for lack of a better term, but it's really a diagonal. Then I would take the sum along this diagonal, which would give me a 6. And I would finally take a sum along this diagonal. The one after that I would continue on to if there was anything there, but there isn't. So working from the leftmost to the rightmost, this would be my product, 1,620. Right, so just to verify, again, I was doing 135 times 12, 1,620. All right. I think a little color goes a long way, so hopefully you found that to be helpful. right? But it's the same idea even for more complicated values. It's a 3 by 3 because I have 3 digits on for my first factor and 3 digits for my second factor. So the setup would be like 3 by 3, and then I would split each set of cells diagonally. All right, so that's just a very quick shorthand way of doing it, but that's how you go about it. All right, so working from left to right against the 8, 8 times 8 is 64. 4 times 8 is 32. 6 times 8 is 48. Move it down the line. This goes down here. Then start over again. Boom, boom, boom. All right, so 8 times 9 is 72. 4 times 9 is 36. 6 times 9 is 54. Move it on down the line. Starting with the 8. 8 times 2 is 16. 4 times 2 is 8. If you want to put a 0 in as a placeholder, you can. 0, 8, just for consistency. You know, the goal-oriented folks out there would be like, you have an incomplete table. Like that table needs to get completed, you know, so I couldn't just have a table that's completed and leave just one entry blank, you know, it just wouldn't feel right. So if you're like-minded in that regard, then just fill it in with zeros. All right, but again, we're going to work our way down each diagonal. So this one's just a 2. Oops, I'm trying to alternate my highlights here. All right, that's going to give me a 13, so carry the 1. I mean, really, when you think about what we're doing here, it's not too far off from the way that we think about math. The difference is that this is a more visual approach, right? So 6, 6, and 12. 6, 6 gives us 12, plus another 8 would get us to 20, so 26. I don't want to accidentally include one of the column headings, so I'm just trying to be careful about that. And in fact, let me get rid of these 2 guys here. Let's see. 1 plus 2 is 3, 6, 12, looks like 14. Double check that. 2 plus 4 is 6, 8, 9, 10, 11, 12, 13, 14. All right, carry the 1. Let's get another color in here. What happened to my color down here? I guess I skipped over it. All right, so that looks like 15. All right, 7 plus 4 is 11, plus 3 is 14, plus 1 is 15. And then the last one would be 7. And again, working our way around the horn here. 7, 5, 4, 6, 3, 2. So 754,632. Do a quick double check. 846 times 892. And there it is. All right, and here's your complete solution. And now you should be ready to go for exercise set 2.2, which is your Egyptian, Russian peasant, and Hindu lattice.